Hey everyone, welcome to Spring One. I'm Jimmy Chunga. Thank you so much for joining us. Really excited to have you all here for reactive applications with Apache Pulsar and Spring Boot with Laurie Otari. So without any further ado, let's just get right into it. Laurie, are you with us?
Yep. Hi, I'm pleased to meet you guys.
It's great to have you here. Let's get to it. Let's jump right in.
And let's do that. I'll share my screen. So I hope you're seeing my screen, and let's go then. I'm talking about the reactive applications with the Apache Pulsar and Spring Boot. And I'm Laurie Otari, a senior software engineer at DataStax. I'm working on Luna streaming powered by Apache Pulsar. I'm an open source contributor from heart. And recently, I'm a Apache Pulsar committer. I have a long journey with Spring, and I've highlighted a few of the most important moments for me in the Spring open source journey. So today, I'll be talking to you about in three different phases. So first section will be about Pulsar and reactive messaging. And then in the second section, we'll go into a sample use case and some live coding. And then the third is about scaling performance of message processing. So first, I'll mention a few favorite properties about Apache Pulsar, what really attracts me. So first of all, streaming, pub/sub, and queuing, they come together in this platform. And this is something like really great. So it's kind of like you get the best parts of Kafka and RabbitMQ in one platform, and you don't have to choose either one. And in addition, you get great performance. And related to that, you have many options for scaling. So it's not just about partitions. So because of the queuing features of Apache Pulsar, you have many more options for scaling your consumers of the application in the system you have. And the third area is that this is a cloud-native architecture. First of all, there's first-class support for Kubernetes. There's a layered storage architecture, which is leveraging Apache Bookkeeper. And then from this, we get stateless brokers. And scaling the system comes with much ease with Kubernetes and this cloud-native properties. So you could scale the brokers separately from your storage. So why would you want to do reactive messaging handling? The first one is that got me into this was that we were building a system with Spring Reactive and Spring Webflux. And when you're doing that, you want to go reactive from end to end. And this is about the compatibility with Reactive Streams. So you get all the promises of what that brings with you. And for example, this non-blocking backpressure. The other part is that for messaging, it's a lot about data transformations. And this approach in Reactive Streams and Project Reactor, it very well fits into this. So when you get to focus on what is the most important for solving your problems. So with this data orientation and this functional approach, it leads to simplification, and the systems you build, they will be easier to maintain. So then yesterday we heard from Josh that the best place to be is in production. And before you go there, you have to be prepared. And to be prepared, you want fault tolerance. And with the Project Reactor, you get fallbacks, retries, and timeouts. And that's part of the preparation before you step into production. And then the other part is that you get resilience with flow control. And that's about the backpressure part. And with a high volume messaging system, I wouldn't dare to go into production without having this. Do you? And then the third area is around performance. Many systems fail because of lack of performance or lack of efficiency. Efficiency means that, or the lack of efficiency means a very high cloud bill. So when you're going to that great place of production, be sure to have this with you. Be prepared. So I'm introducing you to a reactive Pulsar adapter library. This is something that you could use together with Apache Pulsar and Spring Reactive. And this is an experimental project which is currently available at this web address. It's licensed under Apache Software License 2.0, and there's currently some discussions going on where to take this project and eventually. This wraps the Apache Pulsar Java Client asynchronous API with a simple and intuitive reactive API. This is not the final goal to be an adapter library. It would be more optimal to have a true reactive driver, but this is a starting point. And you'll be able to achieve the benefits of reactive streams in Spring Reactive today. And this library goes beyond being just a wrapper. So there's backpressure support for provided interfaces. It takes care of the Pulsar client resource lifecycle management. It has, for Pulsar, there's a concept of a producer resource, and it does some caching for this, which you need in many applications. It has support for in-order parallel processing at the application level, and then finally Spring Boot Starter for auto-configuring a Pulsar Java client, and then this reactive Pulsar client, which is part of this what this adapter library brings you. So what are the reactive messaging application building blocks provided by this library? So there's kind of like two categories for sending messages and then receiving messages. And for sending messages, there is a reactive message sender. And the fine print on the slide, the small fine print, it's about that these abstractions, these don't map directly to the abstractions of the Pulsar Java client. In the properties of these instances, there is such that these are stateless, and that's kind of like part of the nature of reactive streams, that nothing happens until you subscribe, and I'll be explaining that more of that later. For receiving messages, there's two main categories, and then that is the reader, which is something where the application decides the position where to start reading messages, and this position could be earliest, latest, or an absolute or time position. And this is suitable also for short time message polling, like let's say use cases where request response is done over messaging topics. The consumer is meant for guaranteed message delivery and handling. And the the broker will redeliver unacknowledged messages. And this is typically used for always-on use cases, but it's also possible to use this for batch processing or short-time message consuming or polling use cases. And for Spring applications, some of us are used to using, for example, Spring JMS message listener container or the RabbitMQ message listener container. And with this library, there's a kind of like a similar approach for integrating a consumer with the Spring application lifecycle. So some of the basics of a Reactive API. I'm not going into all the details of what Reactive is in reactive programming in Spring Reactive. So we won't have time to cover all the details of that. But we'll look at some of the main characteristics of a Reactive API. So the key thing is nothing happens until you subscribe. And this is something that is very hard to get your mind to kind of like understand this intuitively. So this is the part where the learning curve is very steep in reactive programming. But eventually it's kind of like a simple thing that there's like when you do an API call, it shouldn't be doing any work. It's nothing happens until you subscribe. But you could think of it as the call doing the pipeline, building the pipeline for the reactive streams. And then when you subscribe on that pipeline, that's when the execution begins. And that's the runtime part. So that's the kind of like the hardest part one. But when you grasp that, then you'll get what this reactive programming is about. And this means that all API calls they should be returning reactive publisher types. So for when you're using Project Reactor, it's a flux or a mono. A flux is zero or many, and mono is a 0 or 1 result elements. And then one thing is that also for calls that don't return data, there has to be a reactive, like this publisher type, and monovoid is used for that in Project Reactor. So then going into the interfaces, the Reactive Pulsar Client is kind of like a facade to builders for building these message sender, message reader, and message consumers. And this schema parameter, it's from the Pulsar Java Client. So this is an adapter library. It doesn't try to hide the Pulsar Java Client. So I'm not showing those builder interfaces, but I'll show just the sender, reader, and consumer interfaces. So on the sender, there's simply a send message, send messages. And similarly on the reader, there's read message, read messages. And on the consumer, there's consume message, consume messages. And I'll go more into this method signature of this reactive message consumer later. So that looks a little bit hard, but we'll have a get back to that later. So then we're going to the part where I'm introducing you to this sample use cases. In this, in the use case is a simplified IoT backend. In the story of this project, it's available on GitHub. I've been using that to design the API of this Reactive Pulsar library. So this library is conference-driven development. And without this conference talk, it would have probably taken much longer until publishing this library. But here it is, and the state is still an experimental state, but once we get you to contribute, it'll be much better. But the use cases here are that the first use case is telemetry ingestion from IoT devices, and this is also something that we'll be doing in the live coding. But these other ones, like this telemetry processing, where it's using a message listener container and then consuming messages and then sending messages on another topic. So that you could find in this repository. And then there's an example of sending alerts to a webhook interface to an external, kind of like simulating sending alerts to external application. And then a streaming example with Spring Boot's built-in support for server-sent events. And that's the minimal solution for that is just a few lines of code, but then this one also has the ability to resume from the last consumed position. So when you check that repository, you'll find some code examples, but it's not kind of like best practice code, and that's something that is currently work in progress, like cleaning up and making better examples. So then into the live coding. So I'm just to make it easier to follow the live coding exercise, I'll kind of like show a little bit of this system context for what we'll be doing. And so this is these blue boxes. They're kind of like about the parts of where we will be writing some code. So this is the test code, and this is the kind of like the production code, which we will be testing when we're implementing, or we will implement this, and that's something that we'll be testing. So the plan here is that we would be able to test that when sending a telemetry event, like this kind of like simulating a device, the test receives the telemetry event on a consumer, and it would be going with a HTTP post to the ingest controller that would be sending the message to the topic, and then this consumer will receive it. So that's the plan. So then we also heard from Joss to go to start.spring.io, and we'll be doing a Gradle project, and I'll just call it Reactive IoT Backend. And then for the dependencies, we will be adding the Spring Reactive Web, and then we also want the Lombok. And that's how we generate it. I've already opened an empty project in another window. So this is something that you'll get after opening that up. So this is just an empty Spring Boot project. I have copied a Lombok config file that helps with Jackson deserialization for Lombok. So first of all, we'll start a controller, and we'll call that the ingest controller. And I hope the font size is visible. And here we will first use the annotation to mark it as a REST controller. And this is going to be a Spring Webflux controller. And here we'll we'll be returning a mono void, and this we'll call it this method telemetry ingest. And I'll add the post mapping, and we'll call the endpoint /telemetry. And for this, we'll just start with an empty implementation. And for this method arguments, we will this accepts a flux of telemetry events, and we'll soon implement that one. And we'll use Lombok for this one. And for this, we'll just have a name of the device in sensor path, and then a double value. And in IoT, there's this SenML that I'll just simulate by using these short property names that are typically used to compress the resulting JSON so that it's compact. And now we have implemented that class, and we'll just import the Flux class. And now we have kind of like an empty controller. And then in the next step, we're going to add a failing test case, and this is going to be a Spring Boot end-to-end integration test. So this is in no means this coding exercise something that you should be developing in this way. You would probably want some unit tests and so on, but with this one, we're going directly to an integration test. And so this will be starting this application in this integration test. And by the way, I have started already in Docker. I have Pulsar running here, so that's on this Reactive Pulsar showcase. You'll see instructions like how to start Pulsar in Docker. So here I'll be adding a test case for this that I've finished before. So there's well actually one thing that I missed that we don't yet have the Spring Boot starter imported here. So we'll first go to search.maven.org, and here we'll write Reactive Pulsar, and I've just released the 0.07 version, so that's not yet updated in this UI, but that's currently the latest. So I'll be using that one. So I refreshed the dependencies, and now we should have the required dependencies available. So I'll walk you through this failing test case that I'm added. So we'll soon run this, but first walk through this. So when we take a look at this goal for our live coding, this is the part we're working on right now, and it's this message consumer that I will show you how that is set up. So first of all, in this test, autowired is used. That is fine for using in tests, but don't use autowired in production code. So for test code, that's kind of acceptable. So I've autowired the Reactive Pulsar client. So because this is an end-to-end integration test, it'll also have this Reactive Pulsar client, which gets auto-configured by the Spring Boot starter. So with this Reactive Pulsar client, we're creating a message consumer, and this starts a builder for a message consumer, and on that there's a consumer configurer, and this consumer builder is the Spring the Pulsar Java Client's consumer builder. So the Pulsar Java Client also has a consumer instance and resource. So it's using, this is a wrapper library, and it's not trying to hide it. And the benefit of that is that you could use all the features that are available in the Java client. And then we configure the topic a subscription name in the initial position, and this is that we create this consumer before running the test code, so that this subscription will be created, and it will be guaranteed that it receives, or Pulsar kind of like guarantees that it should receive whatever is added to that topic after that subscription has been created. And there's a special method for creating a subscription. And again, this block is something that it should never be used in production code, and even in test code, it's kind of like questionable. But I'm using it here just for setting up the test environment. So this is kind of like the part that is doing the post. So that's sending that telemetry event. So that's sending that as a post body, and then we're expecting that it's returning an OK value. And then at the end, we'll use the message consumer to consume a single message. And this, I'll be going more into this API, but what this this mapper here, it maps it to a message result. So that's something that this consume message function must be returning. So that acknowledges the message and returns it. And then for testing purposes, Spring or Project Reactor has a test framework, and the step verifier can be used. And with this one, we finally then assert that this telemetry event that we consume from that message, it's something that we're expecting to receive. And now I'll go and run this test case. And we should see a test failure because we have an empty body there, so we don't have any implementation. So as expected, we get a timeout, and the test failed. And so now we have a failing test case, and we're ready to implement the actual implementation. So on this side, we'll be using the reactive message sender, and to get that into use, we'll use construction injection. And here we'll Pulsar Oh yeah, sorry. I guess I don't have the... For some reason, I don't have the dependency here, but let's see if I could resolve this. This shouldn't have happened. It's kind of like a demo thing, but let's try the previous version there. I'll try once more by copying. Well, that worked. I don't know what was going on, but it might have been that I just a few hours ago I published the 0.07 version into Maven Central, so maybe some part was missing, some dependency. I didn't check all the errors, but now it's fine and we could continue. So what I did here is that I used the constructor injection to import or to auto-wire these or inject these Reactive Pulsar Client and the Reactive Producer cache. So these beans are handled by the auto configurer or the Spring Boot starter, and then the Reactive Pulsar Client, we use it to do a builder for a message sender, and on topic telemetry ingest, we specify this producer cache and then build it. And now we're ready to use that in this method. So we'll pass it this flux of messages, and this one will map to this message spec, which kind of like tells the fields and the properties of the message to be sent. So that's a class provided by this adapter library. So this is kind of like a functional approach for defining the message, and then this is the code required for sending this flux with this reactive message sender. And now we will run the test again. And we get it green, so the test passes. So now this means that in this test case we were able to complete this loop. So this completes this live coding part, and I'm sorry about that little glitch about that using that latest version, but this is really on the edge currently. So the last version was published a few hours ago. So use the 0.06 version if you're doing it immediately. But that 0.7 should be available soon. And then we will continue with our presentation. And then going into the third part, and this is also some of that preparation when going to production. As we were talking earlier, that you don't dare to go into production without being prepared. You want to be prepared, especially if you're working with high demand, high volume messaging systems. And we all know that all significant improvements in system scalability come from parallelism. That's something that is also about the CPU cores that we have, that they're not going that much faster anymore. We're getting more cores, we're getting more CPU resources with the cloud. But if we're not able to go and use these resources, it won't help us to achieve performance. And here I'll take a little bit of different aspect. So I won't be talking about the system level, but I'll be talking more about the application level. So that's something we'll get back to. So one extension of the idea of parallelism is pipelining. And one familiar example of this is the HTTP 1.0 pipelining. So the key point here is that the client and the server aren't waiting so much idling. So we will be getting more of the resources that are available. So there's less idling. And it won't be exactly like this in the Reactive Streams and Project Reactor examples I'll be showing about later. But similarly, you will be getting these high gains of efficiency with the parallelism in pipelining. So we will go into some low-level details of achieving this with Project Reactor. And I have kind of like almost like pseudocode level examples. It's not something that you could directly copy paste and run, but I'm walking through the main parts that are needed for doing parallelism and concurrency with Project Reactor. So when you don't have this any strict ordering requirements, when it's fine to process the incoming or the elements on the stream in any order, then this is how parallelism can be achieved. So parallelism is usually recommended for computations, and the difference between the parallelism and concurrency is that on parallelism you kind of like have separate resources allocated for those chains of execution or those execution paths. And for example, you might have a CPU core pinned to that, but then in this concurrency case, it's more about this orchestration, and kind of like an event loop is a good example of that one. So it might be just one core doing that work, but these tasks are in progress at the same time. So they're not necessarily using like separate resources. So that's kind of like how I would explain the difference between parallelism and concurrency. And then so there's kind of like three things to know about on using parallel. So this parallel gives the number of kind of like tracks that will be running in parallel, and then this run on has to be used together with that. And this is kind of like the fan in, the sequential, that all the separate tracks get fanned in. And for flat map, there's it's necessary to use a subscribe on for this inner publisher. There might be also some other approaches for achieving that. So then something about these typically in messaging systems, there is this requirement of processing things in order. And it's kind of like a relaxed ordering, that it's not a total total order over the stream, but within one key, you should be processing those in order. And for this, a typical example of this at the system level is having like multiple topic partitions, and the message is mapped to a specific partition by hashing the key and then taking the reminder from the number of partitions, and that's the partition that is selected. But then if we go into application level, there's also this possibilities of adding some more parallelism. And one example of this is micro batching, that the application takes a batch of elements and then it decides how to process them in parallel. It might do some sorting and grouping and so on. And then the one that I'll be kind of like more focusing on is this stream splitting approach. And there might be in general like some other similar approaches where the application is routing and grouping things, and these are executed in parallel. But here, one approach to do in order processing there is that you map similarly as which was used to select the partition, you have some kind of like concept of a processing group. And I'm talking here about the application level at the single VM that is running somewhere, or a single Spring Boot application. So we're doing parallel processing within that. And this is something that you could achieve tremendous efficiency improvements over a traditional blocking solution, because you could do 100 times or 1,000 times more in parallel with the same resources that have been mainly idling. If your processing parallelism is kind of like tied to the number of components you have deployed. So in this this is well suited, this approach to be used with this Project Reactor's group by. And the benefit over this micro batching is that there's no extra latency caused by batching. And that's many times something that you like, even if the batch is small, it's always a batch, and there will always be some latency to gather up that batch. So in a true streaming approach, you could get rid of that extra latency. So I'm kind of like showing the details here, like how this could be achieved with Project Reactor. And this is also like the approach that the library, this adapter library, provides as kind of like a higher level interface that you don't have to care so much about these details. But I'm explaining this background of the solution, like how it solves this. So when there's a requirement of in-order processing by key, we will be using this group by operator to split by key. And one property of this group by is that you should have a limited and relatively small amount of these keys, the total key space that is available. So if you don't, then typically this means that you shouldn't be directly using, for example, the message key. And I'll show you some solutions for that later on in this presentation. And one guideline in using this is that the concurrency level, this it's shown here, this number 10 here is the concurrency level. That should be set to the total number of groups, or at least to that value or higher, to prevent the stream processing from stalling. In addition, the prefetch parameter of a group by, it's this math max 10 and 32, and obviously that results in 32. that's another parameter that has to be set to prevent the processing from stalling. So I don't know the exact details, but I would assume that it stalls because of lack of demand. But then it kind of like gets deadlocked in a way. So then going back to this, our adapter library, and this with this this was the interface that I promised to come back to this this odd looking method signature. So we'll try to kind of like unwrap this in what this means. So the enabler here is this special signature, and this method accepts this function that takes a flux message as input. So it's a stream of messages coming in, and then this function that you're providing this method, it should be producing a stream of message results as output. And the reason for doing this is that this enables guaranteed message delivery in these, and also the parallel processing, because this kind of like decouples the stream of incoming messages from the time those messages are acknowledged. So the message result that combines the acknowledgement and the result of this this function, or the kind of like the pipeline that this function returns, and the implementation in this library that consumes this message results, and it'll use the Pulsar client library to do the acknowledgements to Pulsar, and then it finally returns this this flux R that can be seen here. So that's kind of like, it might be a little bit hard to grasp, especially if you're new to this reactive programming. But I'm explaining this in detail because that's kind of like one of the keys what enables this parallel processing and at the application level. So that's where you might result or be able to achieve something that you have 100 times less nodes and your cloud bill is much lower. So this in order parallel processing, the implementation details. So to do this, to split this this stream into these ordered fluxes, it uses a key that we mentioned earlier here. This function, this processing group equals hash of the message key, and then the reminder of the number of processing groups. So this is the implementation for that. This function to calculate that. So on a Pulsar message, you have this ordering key, and then you have a partition key, and then there's also the possibility that the message doesn't have any key set. So in that case, it'll use the message ID as the source of this the hashing. And the reason for doing this is that when a message is redelivered, it gets processed by the same processor that initially processed it. So this you don't kind of like mess up ordering also in that case. And there's the actual implementation has been refactored from this, but it's showing the same parts that I showed earlier, like this group by, and then it has this prefetch parameter set to the maximum concurrency, and then it has this flat maps concurrency parameter set to the maximum concurrency. And here this concurrency is it's kind of like a target concurrency parameter, which it'll divide it to that many processing groups. And this is a way how processing kind of like gets decoupled, and still this in order messaging is can be achieved. So I hope you were able to get something out of this talk. I went to very fine-grained details in this Project Reactor parts and how this in-order parallel processing is implemented. But the key takeaway of this is that production is a place that we want to go. But before you go there, be prepared. So it's fault tolerance, it's resilience, it's performance, it's efficiency. You get this when you go to Reactive Streams, Spring Reactive, and this library. So please go to the website pulsar.apache.org and read more about Apache Pulsar and how great it is and how it covers the use cases of both Kafka and RabbitMQ. You can learn more about Spring Reactive at this website. And this library is available here. And it's now the 0.07 version. The API is subject to change until 1.0 is released. So just be prepared. If you're planning to go to production, please contact me. If you're going before 1.0, so then you'll know about the changes that are coming up. And there's this showcase application, and this is also work in progress. And the code hasn't been polished yet, so be aware of that and check the updates on that project as well. And for usage questions, please use Apache Pulsar and Reactive Pulsar tags on Stack Overflow. And you're welcome to join also later on the Pulsar Slack to discuss this library and different matters around it. So thank you, and see you in the Q&A soon.
All right, Laurie, thank you. Great stuff. Very good stuff. And for those of you who have additional questions, you'll know that we do have a Zoom link that has been provided so that you can hop over there and attend a Q&A session with Laurie. And we'll be hearing any additional questions that you may have. So thanks again for attending this session. Your next is coming up in just a few minutes, so stick with us.